Hey guys, I hope you've all been doing well and you've been staying safe and healthy. What I want to do with this video is go over with you the last section, the section that you just went over, 16b, which talks about the order of the atom. Just a reminder that you have a test on Friday that's only going to be over section 16a and 16b. Okay, 16c, which is about nuclear decay, is not going to be on your test, so you don't have to worry about that. I wanted you to read this section as opposed to reading the PowerPoint for this because I just wanted you to get the more specific description, whereas for the different models I thought it would be fine for you just to get the summary. So I'm going to go over this with you. We are going to do some examples of the finding the atomic number and the mass number and things like that. So if you were confused on that, hopefully this will help. If you still have questions, please just reach out to me afterwards. So we're going to get started talking about subatomic particles. Sub, that prefix, generally just means under or smaller. So these are the particles that are smaller than an atom that make up the atom. And you guys know what they are: protons, neutrons, and electrons. You will find out if you take physics and if you take physics related classes later on in college that there are other subatomic particles, but the most important ones are obviously the ones that we're going to talk about now. They're going to be the ones that are involved in chemistry and so on. So for your high school career, these three are fine, but maybe you've heard about quarks before. That's a kind. There's actually a lot, so it's pretty interesting, but we're not going to get into that now. So let's start off by talking about protons. Protons, I use my purple marker here. I drew two little drawings of an atom. You've probably seen an atom drawn like this in like cartoon or something. This might look more familiar from recently. This is basically the Bohr model of an atom. So let's assume that the center here is the nucleus of the atom. We know that protons have a positive charge, right? P for positive. I'm sorry, you can't really see it there. Protons have a positive charge and they're located inside the nucleus of an atom. Okay, so what I'm about to tell you about each of these subatomic particles are the most important things that you need to know. So protons are positive. They're located in the nucleus. They're actually quite large. And they're very stable. They're stable, meaning they're not really involved in reactions and such, and that's because of their location. We know that it's really hard to get into the nucleus of an atom. And it's because of their stability, actually, that they're important in determining the atom's major properties. So protons actually determine what kind of element that atom is. So determine what element. Okay, next we have neutrons. Also remember who discovered protons. I think it was Rutherford. Correct me if I'm wrong. Rutherford discovered protons with the experiment that he did that I sent you a video of, that he was shooting alpha particles at a sheet of metal. Okay, so neutrons. Neutrons are neutral, N for neutral. Neutrons are also located in the nucleus. Remember, neutrons were discovered because when they first only thought the nucleus was made of protons and they weighed the nucleus, they noticed that there was a discrepancy between the mass of the nucleus and the mass of the overall number of protons. The nucleus weighed more than just the number of protons, so there had to be something else within the nucleus that would account for that extra mass. So that's how they discovered the neutrons. It's just another subatomic particle that's within the nucleus along with the protons, that has no charge. Say it's neutral. And they're also big, meaning they weigh more. Not as much as protons, but definitely more than electrons. Let's see. And that's about it. That's what you have to know about neutrons. They're not involved in any sort of reaction because they're just stable. Also, later on in this section, you'll see that an atom of the same kind of element can have different neutrons, or a different number of neutrons. Those are called isotopes, and we'll talk about that in a second. Okay, and lastly we have electrons. Electrons are the main subatomic particle, I guess you could say. It's the one that's involved in the reactions. It's the one that you're going to talk about the most. Electrons are located on the outside of the atom. That's how they're able to be involved in these reactions. That's how they're able to be shared amongst atoms and such. So they're on the outside. They have a negative charge, and they're actually very small. Okay, so I just want to clarify one of the questions that a couple of you got wrong on your quiz. The difference between the Bohr model and the quantum model has to do with, I guess you could say, the location of the electrons. So we know that the electrons are located on the outside of the atom. However, the Bohr model that looks like this said that the electrons are located in these different energy levels, but that their location within the energy levels was like rigid or specific. That's why these lines are drawn. However, we discovered that electrons are never in the same place. They're constantly moving around. So that's why in the quantum model, it was kind of updated to say that electrons occupy a region. So instead of saying electrons occupy this specific place out here on the outside of the atom, we say that they occupy this general region. So they're constantly moving around. So we said protons are especially important because they tell you what kind of atom you have. So each distinctive atom has a unique number of protons in its nucleus. The elements in a periodic table are actually arranged by the number of protons they have. So for example, gold has 79 protons. That's what a number in the top left corner means. If I were to take a proton away from gold, I would no longer have gold. Instead, I would have platinum. Platinum is number 78. For example, rubidium. Rubidium has 37 protons. If I were to take a proton away, it would no longer be rubidium. Okay, protons are what determine what kind of atom or element you have. It's the ID of the atom. Now, that number that I'm referring to is known as the atomic number, or Z. It is not just the number of protons, actually. It's the number of protons and electrons. We've talked about this a little bit in class before. We know that in order to have a neutral atom of a certain element, for example, a neutral atom of rubidium, we have to have the same number of protons and electrons, or meaning we have to have the same number of positive and negative charges so that they cancel each other out and you get a new. I'm sorry, someone called me and my video got cut off. But what I was saying was that the atomic number, which is the number in the top left corner, tells you how many protons and electrons are in that atom. So they have to have the same number in order for the atom to be neutral. But what I don't mean by that is that that number is a sum of them. So you don't have X number of protons in rubidium and X number of electrons, and that in total is 37. What that means is that there are both 37 protons and 37 electrons. Okay, they have the same number so that they cancel each other out and you get a neutral atom of rubidium. Okay, so, and again, that is Z. Z is the atomic atomic number, and it's the number of protons, which is equal to the number of electrons in a neutral atom. We have talked about instances where you have more electrons or less electrons than protons, and that is referring to an ion. We're not going to talk about ions yet, so just assume that the atoms that we are talking about are all neutral, so they must have the same number of electrons and protons. Okay, so next we talked about the mass number and isotopes. So we know within the nucleus of each atom there are protons and neutrons. Now, interestingly enough, every element can have atoms with different numbers of neutrons within it. So in an atom of rubidium, you could potentially have 1 neutron or 2 neutrons or 3 neutrons. Those are known as the isotopes of rubidium. Now, to tell the different isotopes apart, we assign a specific number to them, which is the mass number, or A, and the mass number is the sum. So in this case, you have a sum. Remember, atomic number is not a sum. You have the sum of the protons and the neutrons in the nucleus. So again, the mass number is the sum of the protons and neutrons within the nucleus. But let's say I wanted to find specifically the number of neutrons, so I know what isotope that is. I would do that by subtracting the atomic number from the mass number. So what that is the number of neutrons is equal to the atomic number, which is the protons and the neutrons, minus the atomic number, which is just, you could say, the number of protons. So your book gives you the example of sulfur. So in order to find the number of neutrons in an atom of sulfur, I need to know what the mass number is. The most common form, or you could say the most common isotope of sulfur, has a mass number of 32, and we know that sulfur's atomic number, just by looking at the periodic table, is 16. So how would I find the number of neutrons in this common isotope of sulfur? I take 32 minus 16, and that, I believe, gives me 16, right? Yeah. So just one more time, to find the number of neutrons in the common isotope of sulfur, I take the mass number of that isotope, which is 32. 32 is the number, or the sum of the protons and neutrons in that atom, and I subtract from that the number of protons.